I now call to order the lecture portion of the Society's 2521st meeting in what is now the 154th year since its founding on March 13, 1871. And no, I was not there at that time. Good evening, everyone. My name is Larry. No, everybody knows. My name is Larry Milstein, for the benefit of those who don't know. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry to as broad an audience as possible. So welcome to our members, guests, and friends to the lecture part of today's PSW meeting and to the lecture by Peter Shor on Shor's algorithm and quantum supremacy. What's better than quantum computers? Before we begin, I'm going to thank our sponsors. First, PSW member Mike Helton and Helton Associates, LLC, full-year sponsors. Thank you, Mike. Been a wonderful supporter. And PSW member Joe Schulman and the Schulman Foundation. Thank you, Joe. Another full-year sponsor. And the sponsors of tonight's lecture, PSW members Erica and Bruce Kane, who are here in the audience. Thank you, Erica and Bruce, so much. The Society needs your support. All of this is done by volunteers, and the money goes entirely to support the costs of putting on the lectures. So please, if you have not given or feel you can give more than you have, don't hesitate to donate. It's easy enough to do on the web. Just go to the homepage, pswscience.org, and look for the pull-down menu that has a little tab for dues and contributions. I am pleased to announce the following new members, and I'll have to keep what I say a little shorter than usual because there are quite a few of them. James Rowish, program manager with Northrop Grumman, who learned the PSW from YouTube. Elliot Miller, lead AI engineer with Scilytics, interested in physics, who learned the PSW from Meetup. Joseph Wennerberg, interested in renewable energy, particularly fusion, who learned the PSW from searching the web. Eric Maythorn, medical affairs publication director, who, it doesn't say how he learned of it, so we'll just say he's interested in natural science, physics, space, humanities, and history. Thomas Rabah, interested in physics, who learned of PSW from searching the web. Navtej Singh, a biotechnology student at Georgetown University, broadly interested in science, especially quantum physics, who learned of PSW from me. Sonali Kumari, a research scientist with F-Zeta, interested in cell and molecular biology, immunology, human genetics, and rare diseases, who learned a PSW from me. They're students in the biotech program where I teach, or they were. Paul Jaffe, program manager with DARPA, interested in engineering, space, physics, sociology, who was inspired to join PSW by the previous lecture by Will Marshall. Claudia Gonzalez Viejo, professor of psychology at Ohio University and program director in decision risk and management sciences at NSF, interested in decision-making and risk communication, who learned a PSW from a colleague at NSF, who might be sitting in the front row, but I'm not sure. Robert Lawrence, a CTO at BAE Systems, interested in applied mathematics, information theory, and bioengineering, who learned a PSW from an IEEE email. Ben Dubois, a CTO at Omelas, interested in AI, computer science, nuclear energy, and electrical engineering, who learned a PSW from PSW member Hugh Brooks. Andrew Fiorilla, a software engineer at BlockTech, interested in AI, large-scale computer systems, who learned a PSW from the videos on the PSW YouTube channel. And Peter Shaw, Tonight's speaker learned the PSW from our invitation to him to speak here tonight, and whose interest may be, at least in part, clear from the lecture. Please join me in welcoming them all to membership. All members are entitled to a signed copy of Compendium Volume 17, First Edition of the Bulletin of the Philosophical Society of Washington, a.k.a. PSW Science. If you've not received yours and you would like to get your copy, please come see me after the meeting. It's noteworthy that all members are invited to the pre-lecture receptions and dinners with the speakers for camaraderie and interesting discussions of science and whatever else comes up. So if you're interested in membership, you can access a membership application on the PSW website by clicking the blue Join button on the upper right-hand corner of the home page, filling out the application, paying your dues. That's it, as long as you have a genuine interest in science. You can also take one of those business cards at the back of the room and scan the QR code, which will take you to information about PSW and also to the application form. And with that, Recording Secretary Scott Matthews will now present the minutes of the 2520th meeting and the lecture by Will Marshall on revolutionizing Earth observation with small sats and AI. Scott.
Thank you, Larry. Good evening. On September 5th, 2025, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2520th meeting of the Society to order at 8:02 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, announcing new members, and inviting guests to join the Society. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Jason Dworkin titled, "OSIRIS-REx Brings Samples of Bennu to Earth." The minutes were approved pending a minor correction. President Milstein then introduced the speaker for the evening, Will Marshall of Planet Labs, or Planet. His lecture was titled Revolutionizing Earth Observation with Small Sats and AI. The speaker began by discussing the LCROSS mission, which found significant quantities of water on the moon, indicating that the total cost of the mission was $79 million. For NASA, this mission was, quote, bizarrely cheap. Marshall indicated that the extremely low cost of the LCROSS mission prompted some researchers to contemplate the possibility of even lower cost space missions. He discussed the fact that a modern cell phone has most of the capabilities of a small spacecraft, but cost many orders of magnitude less. The speaker discussed how he and a few of his colleagues formed Planet as a spin-out of NASA with the goal of finding much lower cost ways to build spacecraft. This led to Planet's specific mission, quote, to image the whole world every day and make global change visible, accessible, and actionable, end quote. The speaker described Planet's Dove constellation, using more than 100 small satellites in circumpolar orbits, each acquiring a strip map or line scan of the Earth as the Earth rotates, with 3-meter resolution in 8 spectral bands. 15 additional satellites with 50-centimeter resolution can zoom in on any particular area up to 10 times per day. Marshall said that Planet has been able to do this because of revolutions in the space sector that have occurred over the past 10 to 15 years. These include a 4x reduction in rocket cost and a 1,000x increase in satellite capabilities. He indicated that these factors have led to a huge increase in the amount of Earth imaging data currently available, and that the processing of these massive data sets provides an opportunity for AI. The speaker then described Planet's fleet of satellites, including Dove, SuperDove, SkySat, Tanager, and Pelican. He gave descriptions and performance specifications for each type of satellite, including image resolution, spectral range, sensitivity, swath, and the data products produced. Marshall described specific uses of these data products, many of which utilized AI or machine learning. These included detecting methane leaks, measuring agricultural yields, monitoring deforestation, forest fire prevention by monitoring power lines, measuring drought conditions, and insurance assessment. Marshall discussed the role of Planet's satellites in global security with particular examples from the war in Ukraine. He showed images of a bridge constructed overnight used by Russian troops before and during the initial invasion. He showed how AI could be used to assess damage to individual buildings after bombing and drone raids. He showed how a sequence of previously acquired images allowed authorities to reconstruct the timeline of a mass grave found in Crimea. Marshall emphasized the fact that these images, acquired in near real time, bring an unprecedented level of accountability to modern warfare. The speaker described several public-private collaborations that utilize Planet satellite data for environmental applications. These included monitoring coral reef bleaching, mapping renewable energy facilities, and mapping CO2 and methane, quote, super emitters down to the exact building. Marshall claimed that Planet's satellite data has contributed to more than 3,500 scientific publications and is regularly used by 25 government agencies. The speaker discussed how the AI revolution seeks to solve real-world problems and therefore requires real-world data. He argued that Planet's small sats are providing real-world data in near real time, which will allow AIs to understand the Earth's past, present, and therefore shape its future. The speaker ended his talk by predicting that 3, quote, Copernican moments are likely to happen in the next 2 to 5 years. First contact with AGI, artificial general intelligence, first contact with animals, decoding their communication, and first contact with life off Earth via atmospheric spectroscopy. The lecture was followed by a question and answer session. A new member asked about the size of the data sets being provided by Planet and the computational requirements to query such enormous amounts of data. Marshall responded that huge advances have been made in recent years, specifically citing the example of embeddings, a low-dimensional, dense vector representation of high-dimensional data. He claimed that using embeddings, current systems can search an entire base map of the Earth in under 10 seconds. A member on the live stream asked whether AIs using Planet's data products could detect drones and UAVs. Marshall responded that imaging systems with 50-centimeter resolution can pick up drones and UAVs, and that AIs would have a high probability of detecting them. He indicated that the ability of AIs to detect small drones will almost certainly increase as higher resolution imaging systems are flown in the future. A guest asked how Planet balances the public availability of data with potential privacy risks and the use of data by, quote, hostile actors. Marshall responded, quote, that's a very complicated question and one that we spend a lot of time thinking about, end quote. Marshall said that Planet has an ethics board that specifically looks at these questions. He said that Planet makes distinctions between certified and uncertified users, and that they restrict some of the temporal features of their data during times of war. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures and made a number of housekeeping announcements. He adjourned the 2,520th meeting of the Society at 9:48 p.m. Eastern Time. Temperature in Washington, D.C., 21.1 Celsius. Weather, fair. Audience in the Powell Auditorium, 108. Viewers on the live stream, 26, for a total of 134 viewers. Views of the video in the first 2 weeks, 895. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott. Do we have any corrections or comments on the minutes? Hearing none, I will entertain a motion by a member to accept the minutes as read. Thank you, Bob. Do we have a second? You can second also. Okay, we have a second. All members in favor? All members opposed? Hearing none, the minutes are accepted unanimously and will be posted to the website in due course unless we get something important on the comments on the video on YouTube. So we now turn to tonight's lecture by Peter Shor. Peter is professor of applied mathematics at the Massachusetts Institute of Technology. He has an endowed chair, but it's a very long couple of names, so I haven't included it. Previously, it was at Bell Labs, and he was also at Shannon Laboratories. He's well known for inventing Shor's algorithm, a quantum algorithm for factoring integers, which demonstrated for the first time the potential power of quantum computers. He also produced fundamental work in quantum error-correcting codes, including the first quantum code capable of correcting arbitrary single-qubit errors. You can correct me if I got this wrong. These and other contributions helped launch the modern field of quantum computing. His research interests include the development of efficient quantum algorithms for problems that are classically intractable, investigating the theoretical limits of quantum communication and computation, and more broadly, the interface between mathematics, computer science, and physics. He's an author on more than 100 peer-reviewed publications. Among numerous honors and awards, he has received the Breakthrough Prize in Fundamental Physics, the Dirac Medal of the ICTP, the Gödel Prize, the IMU Abacus Medal, and the BBVA Foundation Frontiers of Knowledge Award. He is a member of the National Academy of Sciences, the American Academy of Arts and Sciences, and a fellow of the American Mathematical Society and the ACM. He earned a BA in mathematics at Caltech and a PhD in applied mathematics at MIT. All questions will be held until after the lecture, during which we will have an extended question and answer session for questions and answers. Peter, the stage is yours.
Okay, thank you. So I will be talking about Shor's algorithm and quantum supremacy. So quantum supremacy is the ability of quantum computers to do things faster than classical computers. And one of the more interesting examples of quantum supremacy is that quantum computers can factor large numbers much faster than classical computers, at least in theory. And I discovered this, and it's now called Shor's algorithm. Okay, so I'm going to say something about quantum mechanics first. So from its conception, quantum mechanics has been recognized as a strange theory. And if you look on the internet, there's all sorts of quotes from the founders of quantum mechanics about how strange quantum mechanics is. And you start looking through them in detail, most of them are apocryphal. These people never said it. I mean, there are some very nice quotes by Bohr on the internet, but if you look at what Bohr really said, it was long sentences filled with very complicated words, and in which he hedged everything, so you can't tell if he really intended what he said. I mean, the first clear statement by a physicist I could find about the strangeness of quantum mechanics is by Richard Feynman in 1964, which is 30 years after quantum mechanics was discovered. And he says, if you simply admit that maybe nature does behave like this, you will find her a delightful, entrancing thing. But do not keep saying to yourself, if you can possibly avoid it, but how can it be like that? Because you will get down the drain into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that. Okay, so how is quantum mechanics strange? Well, one way it's strange is a double slit experiment. And if you spend a particle through a screen with two slits in it, you will observe an interference pattern. And what you can do is you can attenuate the particle beam until only one electron at a time goes through the slit. And you still see the interference pattern. And the obvious conclusion is that what happens is a single electron must go through both slits and interfere with itself. And this is very strange. Okay, so this led quantum scientists to come up with a superposition principle. What a superposition principle says is if a quantum system can be in two distinguishable states, we'll call this A and B, and this funny notation is what quantum scientists use to represent vectors, which are elements of quantum state spaces. So if it can be in both A and B, it can be in a superposition of these states, alpha A and beta B, where alpha and beta are complex numbers with the sum of their squares equal to 1. And when you observe the system, recall we said the system was distinguishable, so there's some experiment which tells us whether it's in state A or state B. The probability of seeing it in state A is the absolute value of alpha squared, and the probability of seeing it in state B is the absolute value of beta squared. And once you observe it, it behaves as if it had been in that state A all along. And this is called collapsing the quantum state, which is really a very informal way of putting it, but this is the actual terminology physicists use, at least sometimes. So the principle can be reformulated as mathematics, and this says a quantum state space is a complex vector space. Quantum states are unit vectors in that space. Two quantum states are distinguishable if they are orthogonal, and a measurement of a quantum state is a projection onto one of a set of subspaces. Okay. So a qubit is a quantum system with two distinguishable states, like the polarization of a photon. If you've played around with polarizing glasses, you know that vertical polarization goes through the glasses and horizontal polarization does not. And that means that there are only two distinguishable states of polarization, vertical and horizontal. And what happens is that all other states can be represented as a linear combination of these two basis vectors. So you have right diagonal, which is horizontal plus vertical, left diagonal, which is horizontal minus vertical, and right circular, which is horizontal plus I vertical. And you can see that right diagonal and left diagonal are orthogonal states because this vector and this vector are orthogonal vectors. Okay, so that's the idea of what a qubit is. And the state space of n qubits are unit vectors in a 2 to the n dimensional vector space. And the huge size of this vector space is one of the places that quantum computing gets its power. Okay. Other very interesting thing about quantum mechanics is entanglement. And in quantum mechanics, you can have systems which are correlated much more strongly than classical laws of probability permit. And such systems are called entangled. And here's an example of an entangled pair of qubits. And this is what Einstein called spooky action at a distance. If you have two such systems, and you assume that the classical laws of probability hold, then measuring one of these systems causes the other to change. However, you can't use these systems to transmit any signals faster than light with them. So maybe what we should do is say that these There's no faster than light transport, and what is different about quantum mechanics is that the laws of probability are different. And I'm not going to go any further into details. So for the first, I guess, 45 years or so of quantum mechanics, nobody really thought of using the strangeness to do anything. In 1981, MIT and IBM sponsored a conference on physics and computation, and Richard Feynman, who is standing somewhere in that neighborhood, gave a keynote address. And this keynote address was titled Simulating Physics with Computers. So in Feynman's talk, he made 2 points. The first was that it seems exponentially hard to simulate quantum physics with classical computers. And the second point was maybe we need quantum computers to do this. Now, it turns out that Yuri Manin had made the same points a year before in the Soviet Union in an introduction to a book on computer science. But Feynman went on to write 2 substantial papers elaborating on this observation, and these papers really led to the development of the field of quantum computation. Okay. There we go. So a number of papers followed Feynman. The first one was by David Deutsch. Now, David Deutsch is a very interesting physicist. The reason that he wrote this paper is to give evidence for the many-world theory of quantum mechanics, which most people think the many-world theory of quantum mechanics is something that cannot be experimentally tested. It gives exactly the same prediction as the classical theory of quantum mechanics. But David Deutsch's idea was, suppose you have an intelligent quantum computer. You can build it. You can ask, do you see the many worlds? And I think the right answer for what would happen if you do that is the quantum computer would say, I don't remember. But, this was a very useful idea because David Deutsch developed the idea of quantum computing by thinking about this. Then David Deutsch and Richard Joseph, who's a computer scientist in England, wrote another paper saying rapid solution of problems by quantum computation. Now, the results are actually much less exciting than the title of the paper sounds, because the result is there's something called the Deutsch-Joseph problem, and they show that it can be solved faster with quantum computation than with classical computation. But this is only if you demand that there is no probability used in the classical computation, and that the classical computation always gives you the right answer. If you let the classical computation flip coins, then this actually, then classical computers can solve this Deutsch-Joseph problem just as fast as quantum computers. So Ethan Bernstein and Umesh Vazirani then wrote a paper about quantum computing called Quantum Complexity Theory. And that's where I started thinking about quantum computation. Umesh Vazirani came and gave a talk at Bell Labs about this paper, and I started thinking about this talk and trying to figure out if there was something useful you could do with quantum computers that you couldn't do with classical computers. But I didn't get anywhere until I saw Daniel Simon's paper on the power of quantum computation. And that paper gave me the ideas I needed to develop the discrete logarithm and the factoring algorithms. So let's continue a little bit. Discrete logarithms. So before I found the quantum factoring algorithm, I found the quantum discrete log algorithm. So the discrete logarithm problem is given a prime p and residues g and r. So its residue is just a number less than p you can think of. Find x such that g to the x is congruent to r mod p. So if you didn't have this mod p, given g and r, find a number x such that g to the x equals r. That would just be the standard logarithm problem, which is very easy on a computer. But this one is much harder than the standard logarithm problem, and we don't know how to do it in shorter than exponential time, which is essentially how long you would take. Okay, so actually we can solve it much faster than exponential time, but still much, much slower than than you would think. So this is, I mean, it's still exponential time, but it's a much slower growing exponential. So this is much harder than the standard logarithm problem. And the interesting thing about discrete log and factoring is that they both can be used for public key crypto systems. Now, public key crypto systems are crypto systems where two people can communicate secret information without having agreed on a key beforehand. So this is perfect for buying things over the internet because you don't want to give your credit card out to everybody who's listening to your internet conversation. So this lets you buy books from Amazon without leaking your credit card to bad actors. So one interesting thing is that there's not a formal reduction of one of these problems to the other. But if you look over history, whenever somebody has found an algorithm for one of these problems, there's an analogous algorithm, which takes around the same amount of time that's been found for the other one shortly afterwards. So they're problems that are connected, but without actually having a formal mathematical connection. And the example for the discrete logarithm problem, remember we have a prime p and residues g and r, and we want to find x such that g to the x is congruent to r mod p. So if p equals 17, g equals 3, and r equals 13, then log modulo 3 of 13 mod 17 is 4. Or I should probably say log base 3 of 13 mod 17 is 4, because 3 to the 4th is congruent to 13 mod 17. So that means that 3 to the 4th minus 13 is a multiple of 17. And you can easily see that's true because 81 minus 13 is 68. Okay. So this is an example of the discrete log problem. So it was by looking at Simon's algorithm that I figured out the discrete log algorithm. So Simon's problem is find the period of a function on the n-dimensional hypercube. So here is a 3-dimensional hypercube, and it's colored. And what we want to do is find a way of going from one point to another point that always ends up with a point of the same color. So here, if we move horizontally one step and then one step in or out of the board, we get to the same color point. So horizontally and then one step into the board You start with a red point. You get a red point, so the period is 1, 1, 0. And here, the discrete log problem can be solved if you can find the period on a large torus. And here you start with a red point. You go 2 to the right and 1 up. You get to another red point. And in fact, 2 to the right and 1 up always gives you a point of the same color. So the period here is 2, 1. So they look similar in some ways. And now I first figured out the case where p minus 1 is a smooth number. That is, it only has small factors. And this case is exactly the case that's solvable on a regular digital computer. However, you might think that this would have discouraged me, but the quantum algorithm was so different from the classical algorithm that it encouraged me to keep on trying. And in fact, this did lead me to a quantum discrete log algorithm. And the basic idea is the Fourier transform. And one thing about Fourier transforms is that they are very good at finding periods. So Simon's algorithm is solved by using the Fourier transform over the hypercube z sub 2 to the n. And discrete log is solved by using the Fourier transform over z mod n, which is the integers modulo n. And basically, once I'd figured out that if you could do the Fourier transform mod z to the n, then you could solve discrete log. What I needed to do was figure out how to implement the Fourier transform on a quantum computer. And it's easy to do Fourier transforms on smooth numbers, which is why I could solve the discrete logarithm for smooth numbers first. And this led to my original scheme for doing discrete log mod p, where p minus 1 is a smooth number. So what it turns out is you can do very good approximate Fourier transforms by doing Fourier transforms just over even 2 to the n, which is a smooth number, but I actually did not figure this out right away. So Alexei Kitaev did, but I did figure out that you could use Fourier transforms to approximate the right steps to find discrete logs. So I want to say news of the factoring algorithm spread very quickly. So I first talked about it in an internal seminar at Bell Labs in April 1994. And in fact, I know this was on a Tuesday because this was Henry Landau's seminar, and that was always held on a Tuesday. But I don't remember which Tuesday it was. It was either the second or the third Tuesday of April 1994. So after I gave the talk, the next weekend, I was in bed with a bad cold, and I got a phone call from Umesh Vazirani, which, if you recall, was the person who wrote the paper that inspired all of my research on quantum computing. And he said, "I hear you can factor. Tell me how you do it." And one thing to note is that the internal seminar, I hadn't figured out the factoring algorithm yet. I'd figured out the discrete algorithm problem, our discrete log algorithm. And that's what the seminar was on. But you recall discrete log and factoring are closely connected problems. And somewhere in this telephone chain, if you know the child games of Whisper Down the Lane, where you say something to the next person and he whispers it to the next person and she keeps it repeating and it comes down to the first person, at which point it's unrecognizable. So something like this happened to turn discrete logarithm into factoring. And luckily, by that time, I had solved factoring. So I didn't even tell Umesh Vazirani that his information was wrong. I just described the factoring algorithm to him. Okay, so that was the first talk on factoring. The second talk was a last-minute invited talk at the first algorithmic number theory symposium at Cornell, which was held May 6th through 9th in 1994. So that was only, maybe 2 or 3 weeks after I gave the internal seminar. And I went up to Cornell and gave the talk, and someone from the NSA came up to me after this and talked to me about it. And interesting thing is that I much later talked to some people at the NSA who had been studying my algorithm, and they had not, and you'd think that they would have heard of the algorithm from here, but no, they heard of the algorithm much later, or I should say a month or 2 later, and this guy from the NSA who went to the talk didn't communicate with his colleagues. Okay. Then there was a Santa Fe Institute conference on quantum information in mid-May of 1994, and I couldn't make it to the conference, but Umesh Vazirani gave a talk on it. And the next thing is in August 1994, at an atomic physics conference in Boulder, Arthur Eckert gave a talk on my algorithm. And I didn't even know who Arthur Eckert and his co-author Richard Joseph was, but they had seen my paper, and they had written a paper for physicists on my algorithm. And so this was what the talk was about. And then there was a quantum computing conference at Gaithersburg organized by NIST, but it's generally assumed that it was actually inspired by the NSA, and they may have given some funding for it. And finally, I published the paper in the Fox conference in Santa Fe in November. So during this summer, I was constantly receiving requests for my paper, and I was sending them out the latest copy. And I was also constantly receiving questions about an error in the old copies I'd sent out, which I had corrected, but I had not corrected in the copies that people previously got. So they were puzzling over these errors. And so it was a very exciting time for me for these few months. And Ignacio Sirac and Peter Zoller are 2 physicists who saw Arthur Eckert's talk in August 1994, and they started thinking about how could you possibly realize a quantum computer. And in November, they published the paper, Quantum Computers with Cold Trapped Ions. Oops, I'm sorry about that. And ion traps are actually one of the 3 or so architectures for quantum computers which are still, viewed as competitive architectures which might eventually, break RSA. And here is what a trapped ion quantum computer at Duke University looks like. If you look, this blue thing, this is a picture, but these little blue dots are not actually part of the picture. They're a blow up of the ions which you actually couldn't see because they're hidden in this slot in this picture. And the ions are held in place by oscillating electromagnetic fields, and they're kept apart because they repel each other. And what you do is you can excite these ions from the ground. I should say they're also extremely cold, so they're, so in the they're in the ground state, except when you deliberately shine lasers on them to excite them. And you use, okay, so there's lots of electronic states of these ions, but you choose two of them. You choose a ground state and one electronic state, and you call the ground state, say, 0 qubit, and the excited state is 1. And you can manipulate the state of a single ion by shining lasers on it. However, you also have to make these two ions interact. And the way that you can make them interact is you shine a laser on one of them, and that excites the ion, but it also starts collective motion of the ions where they're, say, moving back and forth, or they're moving in and out, or something like that. And this collective motion, so you can shine a laser on one that excites it and starts a collective motion, and then you can shine a laser on another which absorbs the collective motion and changes the state if and only if the collective motion is present. And that's how two ions interact. And this is an optical table with lots of components on it. I mean, there are beam splitters, there are mirrors, there are lasers, there's other things. And all of these are designed to act on this little tiny chip with these ions embedded in it. Okay, so since I'm given one architecture, I'm going to give another architecture, and this one I understand much less than the ions, but you use superconductivity to perform quantum computing. So in superconductivity, electrons form Cooper pairs to carry charge without resistance, and here you have a little box which either contains a Cooper pair or it does not contain a Cooper pair. And the qubit is determined by the presence or absence of a Cooper pair. And you get these qubits to interact by putting down something called a transmon, which makes them interact. And again, this is a little tiny chip, but a superconducting quantum computer has this little tiny chip buried somewhere in the bottom, and all this circuitry is used to make the transformations on the qubits from this little tiny chip. And this actually isn't what the computer looks like. This is all contained in a big silver container, which is a dilution refrigerator, and the dilution refrigerator cools it down to within a fraction of absolute zero, which means that you don't get very much noise, and noise destroys quantum computation. Okay, so we have two of the proposed architectures for quantum computer. There were actually many, many, many more architectures proposed at the start of quantum computation, but they were, most of them have dropped. I mean, some of them were quite exotic things like electrons floating on top of liquid helium, but most of these have dropped by the wayside because people couldn't get them to work very well. So there's only a few quantum computer architectures that are still in the running. And The third architecture is neutral atom quantum computers. And neutral atom quantum computers were not viewed as very likely quantum computers until very recently, when a group at Harvard, run by Mikhail Lukin, figured out, I mean, he wasn't the only one, but it was probably one of the main people figured out how to make this work. And what you do is you have an array of neutral atoms which are held and placed by lasers, and you can manipulate them by optical tweezers, and to interact them, and you put these atoms in a Rydberg state, which means that the outermost electron is really much larger than the normal atom. So these are huge atoms. And then to interact them, you take two of them, you move them close together, and because they're close together and their outer electrons are in this Rydberg state, you can make their outer electrons interact, and you can make gates between the two qubits. And again, here is a neutral atom quantum computer, which is, again, there's a ton of optical components on an optical table, and all of these are designed to manipulate this little tiny chip. So this gives you a vague idea of what quantum computers actually look like. Okay, you can ask, are there other advances in quantum algorithms that people have made? And we are actually sorely lacking in algorithms for quantum computers. So one thing quantum computers we know they can do well is they can simulate quantum mechanics. And this was Feynman's original motivation for proposing them. And in the worst case, simulating quantum mechanics can take exponentially long time on classical computers, as Feynman said, but it should be polynomial time on quantum computers, which means quantum computers have a great advantage for simulating quantum mechanics. However, there's a catch. For many practical problems, we figured out clever ways to simulate quantum mechanics much faster than the worst case exponential time. So for these problems, classical computers have a head start on quantum computers, so there may only be a few problems in simulating quantum mechanics which quantum computers are really good at. Now, going back to factoring, Oded Regev has figured out a very clever way to reduce the size of the computations needed to factor. He actually doesn't reduce the total time to solve it, but he takes, say, n² computation and reduces it to doing n to the 1/2 computations for n to the 3/2 each. And the shorter you do a quantum computation, the easier it is to make it stay coherent, which means it will probably work much better than the single long computation of time n². So this may be very useful in practice. I mean, the difficulty is that you really need to look at the details of Regev's algorithm to see whether it will work faster in practice. And when Regev first published it, it looked like it wouldn't, but nowadays people think that it might be useful. And you can ask, are there other advances in quantum algorithms? And there really are not that many. There are a number of optimization problems that it looks like quantum computers might be able to solve faster than classical computers. However, this is still pretty much unresolved. And that's because in the past, quantum researchers have discovered quantum algorithms that were faster than all the other known classical algorithms for that problem. And what happened is once they published their result, classical computer scientists looked at these problems more carefully and figured out how to speed up the classical algorithms to solve them in the solve them just as fast as the quantum algorithms. So it's very dicey to say this algorithm really works better on a quantum computer because we don't have any lower bounds for how fast classical computers can do things. So quantum supremacy is defined by a quantum computer being able to solve a problem faster than could be done by any classical computer. And Google a few years ago announced quantum supremacy. They said they had solved a problem that could not be solved in faster than 20,000 years by a classical computer. And IBM, who's Google's competitor for building quantum computers, then announced, well, we have solved the problem on our supercomputer in only 2 days. And that's because when the Google researchers were figuring out how fast the problem could be solved on a classical computer, they didn't realize that there were some tricks that could be used to speed up the algorithm. And so that wasn't quantum supremacy. Now, factoring a sufficiently large number would be a believable claim of quantum supremacy, but this is probably several decades away in my estimation. Well, at least 1.5 decades away, I think. So we don't really have any confirmed experiments that show quantum supremacy. So one reaction to the factoring algorithm is this is never going to work in practice. And Rolf Landauer did a very eloquent explanation of why not. He says, we have essentially returned to analog computers as foreseen by Asher Perez in remarkably perceptive comments made in 1985. Analog computers can do far more per step than digital computers, but they cannot take very many steps before the accumulated errors derail the computation. And my summary of this objection is that quantum computers are essentially analog, and analog computers can't correct errors. Now, actually, I came up with a refutation of this objection shortly after, maybe a year or so after he made it, and that is that just like quantum objects, which are both waves and particles, quantum computers are both analog and digital. And their digital incarnation, they can correct errors. And in their analog incarnation, they can do amazingly good computations. And I'll explain this statement shortly, but I can ask, how bad is the situation? Well, to factor cryptographically important numbers, you need to perform something like 10 to the 9th quantum gates. That means you need to implement each gate with accuracy less than 10 to the minus 9th in order not to derail your computation before it terminates. And this strikes experimental physicists as utterly impossible. And of course, there are computations that would require many, many more than 10 to the 9th gates. I only picked 10 to the 9th because this is roughly what you need to factor 2,000-bit numbers, which are the numbers that are cryptologically important and would break most of the crypto systems used to communicate over the internet. So we can ask, can we use error correction? So in the 1950s, von Neumann showed that you can perform noise-free computation with noisy gates without too much extra overhead. So we can ask, can we use his or similar techniques? And one of the reasons von Neumann was thinking about this problem was he was thinking about the brain and how the brain obviously had a lot of noise in it, and it still gave good results when you did a computation with it. So at first glance, it appears that the answer was no. And the question, so we can ask why. Oh, come on. it turns out there are two no-go theorems. There's the Heisenberg uncertainty principle, which says any attempt to measure an unknown quantum state inexorably disturbs it. And there's the no-cloning theorem, which says you cannot duplicate an unknown quantum state. Okay, so what goes wrong? Well, what von Neumann's technique does is it duplicates each bit of the computation k times. So what we have to do is we have to correct the state if one of these k computations, I mean, you can think of this as, say, I mean, we have k correct copies, we have k minus 1 correct copies of a bit and one wrong one, and we'd like to turn that into k copies of the bit. So what we need to do is you need to reconstruct k copies of an unknown qubit from k minus 1 copies. And reconstructing 2 copies of an unknown qubit from 1 copy is cloning, which we know is impossible. And you can just look at the proof of the no-cloning theorem and say that reconstructing k copies of an unknown qubit from k minus 1 copies is also impossible. So von Neumann's technique won't work. So a number of other classical techniques for fault tolerance fall victim to the same problem. Can somebody say how much more time I have? However much I need. Okay. Okay. And I want to know why this clicker is not behaving reliably. So error-correcting codes also appear to require redundancy and thus to violate the no-cloning theorem. So error-correcting codes are another way we make classical computation fault-tolerant. However, it turns out that error-correcting codes can be made to work and provide quantum fault tolerance. So let's go back to a short tutorial on error-correcting codes. So the simplest classical error-correcting code is the repetition code, which has been known for centuries, if not millennia. And that's, you just take every bit and you duplicate it many times. So I'm using 3 here, but really you could use 17 or any number you wanted. And you can ask, what about the quantum version? Well, here you take a qubit, 0, and you make 3 zeros, and you take a qubit 1, and you make 3 ones. So if you've been paying attention, you might ask, isn't this a quantum cloner? And the answer is this is not a quantum cloner. So this transformation turns 1 over root 2, 0 plus 1, so this is a superposition of 0 and 1, into a superposition of 0, 0, 0, and 1, 1, 1. When really, if you wanted to do a quantum cloner, you would have to do 3 copies of a superposition of 0 and 1. So it's not a quantum cloner. And in fact, there's a very simple quantum circuit that does this repetition code. Okay. My clicker's not doing anything half the time. Okay, so this works against bit flips. So a bit flip is when it's, this matrix sigma x is a bit flip, so it turns 1s to 0s and 0s to 1s. And what you can do is you can measure which bit is different. And the possible answers are none, bit 1, bit 2, and bit 3. Okay. And after the measurement, the state has collapsed. So the answer is really the correct state. Thank you. So when you have measured the state and it's collapsed, what you can do is you can either apply the identity matrix, which does nothing, or you can... Okay, so this is a different kind of mouse. There we go. You can apply the identity matrix, or sigma x, to the first qubit, sigma x to the second qubit, or sigma x to the third qubit to correct the error. So mathematically, how do you measure which bit is different? Well, what you do is you project onto one of the 4 subspaces. This subspace is the subspace with all 3 qubits alike. This is the one with the first one different. So this is the one with the second one, and this is the one with the third one. And it turns out these 4 subspaces are have the properties that you can measure them with a quantum operator, and you can actually even come up with a simple quantum circuit that performs this measurement. Okay. So this also works for superpositions of encoded zeros and ones. So assume we have the state, a superposition of 0 and 1, and we have a bit flip on the second qubit. When this is measured, when we measure this state, we get the result bit 2 is flipped. And now, since the measurement gives the same result for both elements of a superposition, we do not collapse the state, and the superposition is not destroyed, and we remain with this superposition, which has an error in bit 2, but now we can correct it. We know the error, and we know which bit is in, so the quantum state can be corrected by applying a Pauli x to the second qubit. So this was realized in Asher-Perez in a very prescient 1985 paper titled Reversible Logic in Quantum Computers. And in fact, this is the paper that Rolf Landauer was referring to in his statement about why quantum computers can't work, or why you can't correct errors in quantum computers. So it turns out that to do quantum computation, you need to correct more than bit errors. You also need to correct phase errors. And what phase errors do is they keep the quantum computation coherent. And so here is a sigma z error, or sigma z Pauli matrix, and this applies and makes the phase of the first qubit 1, and the phase of the second qubit, it changes it to -1. Or I should say it multiplies the phase of the 0 qubit by 1 and the phase of the 1 qubit by -1. And Asher-Perez didn't worry about phase errors because all he was trying to do was implement classical reversible computation on a quantum computer. And the 3-bit quantum repetition code, you can ask what happens when you have a phase flip error. Well, if you have a phase flip error on any of the 3 qubits, what it does is it applies a minus sign to the qubit with a 1. So that means the 000 plus beta 111 goes to alpha 000 minus beta 11. So this is a valid encoding of the state alpha 0 minus beta 1. So now we've made a phase flip error on the encoded qubit. And a phase flip error on any of the 3 encoding qubits gives a phase flip error on the encoded qubit. And this makes phase flip errors 3 times as likely. Now, there's something I realized, which is there's a Hadamard transformation, or this 2x2 matrix, which is a transformation you can apply to a qubit. It's called a Hadamard transformation, and it takes bit flips to phase flips and vice versa. And if you apply the Hadamard transformation to the 3 encoding qubits and the encoded qubit, what you get is the new code, whereas 0 gets mapped to a superposition of elements with an even number of 1s, and a 1 gets mapped to a superposition of elements with an odd number of 1s. And we have a mistake in there. The last thing should be 001 and not 011. Okay. Oh. So if you have a bit flip, it takes an even number of 1s to an odd number of 1s and vice versa. So now bit flips are 3 times as likely in this code. But any single phase flip can be corrected, and we took our code that corrected bit flips and made phase flips 3 times as likely, and we applied a transformation to it that flipped qubit bit flips, which, turned bit flips into phase flips and vice versa. So it's perfectly logical that bit flips are now 3 times as likely, but phase flips can be corrected. So what do we do? Well, we have 2 3-qubit codes. One of them corrects bit errors, but makes phase flip errors more times as likely. The other corrects phase flip errors and makes bit flip errors 3 times as likely. So it seems like we're stuck. We can improve its performance on bit errors, but that makes phase flip errors worse, and vice versa. But we have, we want it to protect against both bit flip errors and phase flip errors. What do we do? Well, we use this, come on. We use this technique that classical coding theorists know very well, and we concatenate the 2 codes. So first we encode the quantum state using one 3-qubit code, and then we encode each of the 3 resulting qubits using the other 3-qubit code. And now we get a code that protects against both bit flip and phase flip errors. And this was the first quantum error correcting code discovered. And what does it look like? Well, step 1 is we encode using the outer code, which is the phase flip code. Of course, that's completely arbitrary decision. We could have used the bit flip code first. And then we apply the inner code to each of these qubits, and that gives us this 9-qubit code. And you can check that it will correct any phase flip and also correct any bit flip. And since it can simultaneously correct one phase flip error and one bit flip error, it can also correct a sigma y error, because sigma y equals I sigma x times sigma z. And this is a 9-qubit code. So how did we get around the Heisenberg uncertainty principle that any measurement of the system disturbs the quantum state? Well, what we did what we did was we found a code where you can measure the quantum state without disturbing the encoded state, and we did that by making the encoded state and the errors orthogonal. And you can ask, how about arbitrary errors which are not sigma x, sigma y, sigma z? Like measurements are arbitrary unitary operators. And the theorem is, if you can correct any error in a single qubit that is one of the 3 Pauli errors, then you can correct an arbitrary error that is restricted to 1 qubit. And that's because an arbitrary 2x2 matrix can be expressed as a linear combination of the 3 Pauli matrices and the identity. And you can think of the error as being in a superposition of the 3 Pauli errors. Now, when we measure the error, we collapse the state so that the error is one of the 3 Pauli errors. So now we can correct it. So is this a paradox? Is information, one of Rolf Landauer's favorite aphorisms was information is physical. So we can ask, is information really physical? Well, we can encode 1 qubit into 5 qubits and then decode it. And even if one of the 5 qubits is destroyed, it decodes to the correct state. So we can ask, where was this qubit? Where did the qubit live in the middle of the quantum circuit? Well, it can't be in any single one of the qubits, because then it would get destroyed when we destroyed that qubit. And by the no cloning theorem, there can only be one copy of it. So it must somehow implicitly be encoded by the entire collection of qubits. So, I mean, this information is not exactly really physical. Okay. So while the repetition code has been known for centuries, better classical codes were not discovered until 1950, and the first classical code to be discovered were Hamming codes, and here's the 7-bit Hamming code, which is the first, simplest Hamming code. So what I did was, with Rob Calderbank, is we adapted the classical Hamming code to a quantum code. So 0 goes to superposition of 8 of the code words of the Hamming code, and 1 goes to a superposition of the other 8 code words of the Hamming code. And this corrects one bit error, because since we started with a classical Hamming code, if we have 1 bit error in here, we can correct it, and we correct it basically using the same circuit we would use to correct a classical Hamming code. And it also corrects one phase error, because remember we had this Hadamard transformation that flips bit errors and phase errors. And when we apply this Hadamard transformation to this code, we get the exact same code back. So that means that we can now correct one phase error, since the code is exactly the same as the bit space and the phase space. Okay. And the quantum Hamming code was discovered independently by Rob Calderbank and me, and also by Andrew Steen. It's the smallest code in the class of CSS codes, which was named after the discoverers. And a CSS code is really a quantum error correcting code based on 2 classical error correcting codes, C1 and C2 dual, with C2 contained in C1. And C1 corrects bit errors, and C2 dual corrects phase errors. And the nice thing here is that classical coding theorists had compiled exhaustive lists of classical error correcting codes. And we could look at these lists and find a vast number of quantum error correcting codes. So we get a ton of quantum error correcting codes. Of course, what we really want to do is we want to get fault-tolerant protocols for quantum computers and not error correcting codes, because fault-tolerant quantum codes for quantum computers, so quantum error correcting codes can take a quantum state, transmit it over a noisy channel, and then decode it. But if you have 2 qubits encoded in a quantum code and you want to perform a gate on them, you've exposed them to error. So what you have to do is you have to figure out how to do fault-tolerant gates without decoding your qubits. And there are good quantum codes you can use for fault tolerance. And I want to talk about 2 of these, and then I think I want to end my lecture. So first one, class of codes, is surface codes. And these have the property that they're planar. So most gates are between 2 qubits that are close in space. And these are very good for superconducting qubit architectures. And the disadvantage is that each encoded qubit needs 49 or more qubits to encode it. So you end up needing massive numbers of qubits. And LDPC codes, these codes are much more efficient in terms of numbers of qubits. However, they also have higher connectivity. So to decode these codes, you have to use a lot of gates that take 2 qubits that are far apart and make them interact. And that's very difficult to do on superconducting qubits. So, and remember, okay. I have a whole bunch more slides, and I think I want to skip through them. So, what would really be useful for making quantum computation work in the long run? Well, first is we'd like to find new quantum algorithms that solve different problems and not the ones we already know how to solve. 2 is we want to improve our current quantum algorithms. So Regev improved the factoring algorithm. There are a number of other ways you can improve the factoring algorithm, although none of them are as dramatic a change as Rege's. And we finally wanted to find better ways of performing quantum fault tolerance, because if you could find an optimal way, so performing quantum fault tolerance, it reduced, finding better ways of performing quantum fault tolerance. I think it has, a few years ago, someone did an analysis and it said you could do factor numbers with, 30 million qubits. And recently they've done a new analysis, and you can factor numbers with only 1 million qubits. And I think a lot of the difference between these two analyses were that we now have better ways of doing quantum fault tolerance, and and that can reduce the time on a quantum computer by an order of magnitude or so. So this is what we'd really like people to do in the future. Okay, thank you.
So we do have time for some questions. We may not go as long as usual. There is a procedure for the questions. So the blue microphone, if you'll stand up, tell us your name and if you're a member.
Hello, I am Fiona, and my question is, I am but a undergraduate student studying electrical engineering. What can I, what are next steps from here?
Oh, so
That's a mentor question.
right. So I have a couple of pieces of advice. First, you should take quantum computing classes, and if you can. Second, it seems that pretty much any field of math or physics might be useful for quantum computing. So if there's a math course you want to take, like maybe representation theory, representation theory is useful for quantum computing. If there's you could take quantum field theory, that's useful. You could take statistical mechanics, that's useful. So just learn the pieces of math and physics that you're most interested in, and then you'll have some more background for quantum computing. And we also really need quantum computing engineers, so learn engineering.
Are there any online courses you would recommend out of MIT?
So there's a quantum computing there are 2 quantum computing courses in edX from MIT. I don't know whether they're running or not, but you could check them and see if someone's running one of them, and then you could take it. And there are 2, actually, I want to say that there are 2 versions of these courses. One is really quite expensive and intended for, engineers at companies, and the other one is free. So if you're an undergrad, you can probably take and you can find the free one online. That's good. And I'm sure there are lots more quantum computing courses you can find online. My notes for the first course in quantum computing are actually online as well.
Red microphone, please stand up, tell us your name, and if you're a member, and ask a question.
Hi, my name is Barak Dayan. I'm from the Weizmann Institute, and I'm one of those who is trying to build a quantum computer. We have a quantum computing company, Quantum Source, and I have 2 questions which are actually related. On the bigger scale, do you believe in quantum computation? And in more precisely, if Shor algorithm is good only for factorization and is actually the only algorithm that is proven to have significant speed up, why should we bother? Or maybe Shor's algorithm is good for many other things, not only factorization. So.
Yeah. Well, my standard answer to this question is if you look at the history of classical computer scientists, many of the most useful algorithms would never have been discovered if people hadn't been experimenting on classical computers. For example, the simplex algorithm for solving linear programming, if you look at it, there's no way that you can prove that it runs in less than exponential time. I mean, so this has been proved, I think this was proved around 2000 and it was discovered in 1950s. So if, if someone had discovered it and it had been, people were unable to run it, they would have done this computation to say, in the worst case, this is exponential time algorithm. Why should we even consider it? And so it never would have been discovered, or at least it never would have been adapted. So what you really need to do to find algorithms for quantum computation is take quantum computers and experiment with them and see what you get. And we can't do that yet because quantum computers are too slow.
And is Shor algorithm good for other things other than factorization?
So there are a bunch of number theory problems which are not anywhere near as, have nowhere near as financial interest as factorization, but there are a bunch of other number theory problems you can use Shor's algorithm to solve.
A blue microphone. Stand up, tell us your name, and if you're a member of PSW. It's okay if you're not. I just want to know.
Yeah, I'm Adam and not a member. I wanted to ask, are you aware of any interesting applications of quantum computing outside of cryptography?
Well, I mean,
Just said.
one possible interesting application is to simulating quantum mechanics. So right now, one of the heaviest users of computation are pharmaceutical companies, and what they're doing is they're using computation to figure out how molecules behave, and that is really an essentially quantum mechanical question. So if you could somehow find ways to speed up this process with a quantum computer, you would have a huge market for them. Unfortunately, we're nowhere near having good algorithms for molecular simulation with a quantum computer.
Red microphone.
Matt Kaywood, member. Professor, some of us are familiar with the uncertainty theorem and so on, maybe less familiar with the no cloning theorem. Can you give a little more intuition on kind of how that works and maybe why it doesn't apply to these kind of redundancy codes? Is it because the state space is expanding? I'm just struggling with that a little bit.
Yeah, so the no cloning theorem says, suppose you have an unknown qubit. The transformation that takes you from one copy of the state psi to two copies of the state psi is not one that can be made physically. On the other hand, if you have two copies of a classical bit, or one copy of a classical bit is either 0 or 1, it can be turned into 0, 0 and 1, 1 very easily. And this is what the error correcting code transformations do. They essentially operate on bits, on qubits classically. So you have a 0 goes to two zeros and a 1 goes to two ones. But a superposition of a 0 and a 1 does not go to two copies of the superposition. It goes to a superposition of two zeros and two ones. So this is not a cloner. It's essential. It duplicates a classical bit that represents a quantum state. So that can be done, and The amazing thing is that this actually is useful for giving quantum error correcting codes.
And maybe we can get the red microphone over to Richard. And we'll go to the blue microphone, wherever it is. Blue microphone.
Hello. So,
Name.
Elliot.
Are you a member?
I am a member. You actually announced me. Uh, so this is actually a huge honor for me because, again, I studied quantum computing very briefly in grad school, specifically for topological quantum computing. Since then, I had learned about Shor's algorithms and have been learning about quantum algorithms from various places, especially from IBM Qiskit. The burning question I've always wondered is that I think Shor's algorithm is particularly unique because while the prime factoring problem isn't truly NP-hard, it's still a very hard problem of which is converted into a much more easy problem via a quantum algorithm. Similar algorithms like Grover's algorithm only give you like a linear to square root speed up. And the open question is this such a unique situation with prime factoring that is only solved by your algorithm, or is there truly another Shor's algorithm out there that could provide the possibility for such a monumental quantum speedup?
Well, I would really like to know the answer to that question. I mean, there are some other algorithms that people have claimed give a exponential speed up. I think I'm trying to remember what these are. I mean, one of them recently was decoded quantum interferometry or something like that. And it's still controversial whether this really is a better quantum algorithm or not.
Yeah, I've heard they're all like special cases, or they're all for extremely specific circumstances. It's only really Shor's algorithm that has the verifiable quantum speedup.
I guess there wasn't actually a question there, so let's go to the red microphone.
Yes, my name is Richard Talbot. I'm a proud member of PSW. I have supported the U.S. Navy in analyzing your technology. I had to immerse myself into it. And sir, I sit at your feet, paper and pencil in hand. Question for you would be, classical computers are organized as words, a horizontal word, and then many layers of those words throughout the silicon chips. What's the optimal organization in a quantum computer to do your algorithm?
I mean, you can also organize quantum computers in words, and very similar to the way that you can organize classical computers. And what's the optimal way of doing my algorithm on a quantum computer? Well, really, I mean, the way we organize classical computers isn't because these are the optimal way of organizing them. It's because they're a way of organizing them that we can easily reason about and program with. If you want an optimal algorithm, what you have to do is you have to look back in the early days of classical computation when computers were very much more primitive than now, and people programmed really in machine code rather than in programming languages. And they did all sorts of very interesting things to make them run faster. And right now, we're probably at this stage in quantum computers, but what we really need to do is to find ways of organizing quantum computers so that we can think about them and program them easily. And they're probably going to look a lot like the ways we organize classical computers.
Would you expect to entangle the bits?
Yes,
From
I'd
word
expect
to
to
word?
entangle the bits.
All the way through, okay.
Well, it depends on the algorithm, but maybe all the way through.
Okay, thank you.
Let's try to get the red microphone up here to the gentleman in the green shirt, and then we'll go to the blue microphone while that's happening.
Yeah.
Name, are you a member? of
I'm a
PSW?
member. My name is Mark. And I have a question about the factoring algorithms. And I'm curious whether there's a connection between that and problems like the Riemann hypothesis. Does this present new approaches to solving that problem?
Well, I wouldn't think so, because the problem with the Riemann hypothesis is we have to come up with a proof. And proofs are fundamentally classical objects. I mean, and it's possible that a quantum computer could discover a proof of a Riemann hypothesis, but it would still have to be a classical object at the end, and we don't have any good ways of making quantum computers spit out proofs.
Red microphone.
Hello, my name is Mark Parrish. I'm not a member yet, but will be soon.
Excellent.
I quickly wanted to also say thank you for your open courseware notes on your website for your quantum computing course. They're concise and fascinating in a way that not many things are. To do something actually useful with current or near future quantum processing units, does it make more sense to consider them in the context of GPU architecture that performs many simple operations, maybe with limited vector dimensions, in parallel? I was thinking quantum discrete element analysis, but you mentioned a second ago that we don't have an algorithm for quantum mechanic interactions yet.
Yeah, well, I don't know. I mean, I think that's an approach that's definitely worth trying, but I'm not sure whether it's going to succeed or not.
Thank you.
Blue microphone.
Hi, my name is Twesh. I'm a PhD student in quantum information theory, and I'm not a member. Thank you very much, Peter, for the talk. My question to you was, you seem somewhat optimistic about potentially finding quantum algorithms in the future that, like Shor's algorithm, give a lot of speed up on a problem that is classically very slow, either provably or just by the best algorithms we have. In a very broad sense, what kinds of questions in mathematics do you think might be amenable to finding these kinds of faster quantum algorithms? Thank you.
Yeah, well, the reason that discrete log and factoring can be sped up is that they have very interesting structure within them. So I think what you want to look for is problems with an interesting mathematical structure which somehow can be used to find a quantum algorithm to speed them up. I mean, there's a lot of problems without structure, and I don't think you'll find a way to speed them up on a quantum computer faster than a square root speed up. I mean, Grover's algorithm solves the search problem, which doesn't have any structure, and you can't speed it up more than the square root of n speed up that Grover's algorithm does. So I think structured problems are the ones you have to think about.
Red microphone.
Hello, I'm Ginger Greenfield. I'm a member, and I really appreciate your talk. I actually graduated from Cornell University in 1994 in May. I was there. I took topology.
Question.
Okay, my question. And from graduate school at Oxford, I know quantum computing people who were in Russia. So my question is, what's going to be useful for humanity? Like, what now for us? And I am actually a parent. It's like, what for the next generation, for kids, for like students? I mean, you're a professor, right? Like, what do we want to do for humans on the planet with quantum computing? I love the beauty
I think
of
we got
mathematics.
the idea.
Okay, so, I mean, there's a lot of physics questions which we don't know the answer to, and which it's possible quantum computing will tell us the answer. For example, high temperature superconducting would be incredibly useful if we could find materials that had superconductivity at high temperature. And right now, if you give us the Hamiltonian that acts on a chemical system or a condensed matter system, we don't know whether it gives us superconductivity. And if we had a quantum computer, we could put this question in a quantum computer and we could tell whether it gives us superconductivity. And then maybe we could figure out what what causes superconductivity and the mechanism behind superconductivity. And maybe if we were clever enough, we could find a high temperature superconductor once we knew these things. And that would be a great advance in, for humanity. Of course, it's possible that, high temperature superconductors just don't exist. So so this may be a vain hope, but it would still be very nice to know what makes things superconduct.
I'm going to take two more questions and then we will close out. I think blue microphone back, the red microphone.
Yes, thank you. I'm Matthew Wilson. I'm not a member. Considering it has not been proven that you actually have to solve the factoring problem or the discrete log problem to break, those crypto systems, have you ever heard of any other approaches other than solving that hidden subgroup problem for finite abelian groups?
I think that to break RSA without factoring seems really incredibly unlikely to me. So, you can't formally show that factoring is equivalent to breaking RSA, but I don't see any route to break RSA without factoring.
Last question is blue microphone.
Oh, hi. My name is Min.
Are you a member?
I am not a member, unfortunately.
Thank you.
Look into it. So I just wanted to ask. Last time when I was looking at this, I was a graduate student studying cryptography, and it seemed like if I remember correctly, the class BPP is a subset of the class BQP, if that is still correct. Have you seen any discoveries to say that that is no longer the case, or have you seen any kind of reduction between BQP to one and B-complete problems?
So the classes you're asking about are BQP and BPP?
Yeah, have you seen any evidence to suggest that perhaps BPP is a strict subset or equal to BQP?
The fact that you cannot factor with with a classical computer that has a random number generator is, or at least that nobody knows how to factor with a classical computer that has a random number generator, is evidence that BQP is strictly harder than BPP. But I think you're looking for more rigorous proof-based evidence, and I don't know of any.
Thank you.
Well, that'll be the last question, but we will be adjourning to the social hour. So there is some time in addition to have a discussion and answer questions. Let's thank our speaker. Before you go, we have a few gifts for you, which I'm just going to show. They are actually, the real things are actually here. One is a framed copy of the announcement of your talk, signed by all the members of the General Committee on behalf of the membership. Another is the PSW ribbon, which is emblazoned on its side with stripes that are evocative of the symbol for the Henry, which is named for the founder of PSW, Joseph Henry, who is well known for having elucidated principles of inductance, and for whom the unit of inductance is named. And then a copy of volume 17, first edition of the PSW Science Bulletin, which brings together many of the original founding documents, lists all of the original members, sets out why the organization was formed and what its purposes are. Also has 3 histories of PSW and has some of the abstracts of some of the more interesting talks, which are paired historical abstracts with modern ones. For instance, the talk that revealed for the first time what the vector formularia is was presented here at PSW. And then, I don't know, maybe 100 years later, we had a talk on genetically engineering mosquitoes so that the parasite of malaria it can't take root in them, and so they don't transmit the disease. And there are several of those kinds of things that show a kind of continuity that you might not expect in what kinds of subject matter interest science. So with that, I'd like to thank you very much for spending time with us. Our next lecture will be at the 2522nd meeting on October 3rd. And the speaker will be Adam Rees, professor of physics at Johns Hopkins University and co-recipient of the 2011 Nobel Prize in Physics for discovering that the expansion of the universe is accelerating. Currently, the 2 major approaches to determining the Hubble constant give significantly different results. And since that was originally seen, refinements in both measurements have further converged to their differing values. The difference is referred to as the Hubble tension and will be has fueled speculation among astronomers and cosmologists that we don't really understand what's going on. Now, let me remind you, this is coming from people who say that, what is it? I'm going to get the numbers wrong. 25% of the universe is dark matter. We don't know what it is, and everything but 5% is dark energy, and we don't know what that is. And now they're telling us we don't even know that. No, I'm just kidding. But physicists maintain they know everything. So this will be a very interesting talk, and he'll discuss the tension and what he thinks it might mean for new physics and cosmology. He previously gave a lecture at PSW's 2261st meeting before he won the Nobel Prize in 2009. There's written minutes of that talk on the PSW website, but it was before we started recording lectures. You also might want to take a look at Wendy Friedman's lecture. She discussed the Hubble tension at her talk at the 2428th meeting on November 6, 2020. And there is a video of Wendy's talk on the PSW website. It was by Zoom during COVID. Other upcoming lectures are on this slide. For those of you who are keeping track, please note that November 22nd, Cal Newport has canceled his lecture. I'm not going to go over these, so just note that about 10 days in advance of all events, PSW sends all members invitations to the pre-lecture reception and dinner with the speaker, and notices of the lecture itself, by itself, go to everyone on the PSW friends list. Feel free to join PSW. Feel free to sign up for the lecture notices on the website. You can link the PSW calendar to automatically populate your PIM if you like. And with that, let's thank the people who did the cameras and set all the equipment up. And with that, I will accept a motion from a member to adjourn the 2521st meeting to the social hour. Second? All in favor? The meeting is adjourned to the social hour. Thank you all for coming.